biceps, which is this one here, which allows you to lift full pitchers and stuff, or weights, or whatever, are made up of many single fibers, and these fibers are long, elongated cells. Each fiber is a long, more or less cylindrical cell, and it can be about 1 centimeter or millimeters to about 120 millimeters in length. And of course, if you're 6'12" or something long, then of course it is longer. It depends on the size of the individual. This is just in general. Now, one other thing I want to point out now. I'll give you a lot of numbers. Don't memorize the numbers. Please don't memorize. I don't want to know that this is a muscle that's 1.6 kilometers in length. Not interested. So general principles only. Don't memorize numbers. This is just for illustration. A long cylindrical cell, and it varies in diameter. Now, generally, once you are born or you reach adulthood, you don't get few muscle fibers, but what happens when you work out is the little ones get bigger. Now, each muscle cell ends in tendons made up of a fibrous inelastic tissue composed largely of collagen. That's where it attaches to the skeleton. And fibers themselves are made of the smallest subunits arranged in bundles, about 5 micrometers in diameter, which are called rods or myofibrils. And each of these is about 1.5 to 1 micrometer in diameter. And these will, of course, be the same length as the muscle. Here's a picture I stole from some textbook. It's in every textbook in physiology that I can remember, showing you a big biceps with a bundle of muscle cells. These are the individual cells. Our muscle, there's a bunch of cells in this one here. These turn out to be the individual cells. And the smaller units which make up the cells are the myofibrils. And there make up this unit. So that's the structure of muscle, starting from a bundle of muscle cells, individual cells, and then you can go to rods and myofibrils, which are the smallest units of muscle. These muscle cells are actual cells. They have resting membrane potentials. You know what those are. And these, of course, are the subunits which make up the muscle cell. Now, the other thing about skeletal muscle, it's multinucleated. Because they're long cells, and you need to have nuclei all through the cell. Now, the functional organization, I think Dr. Noyan would have brought up before. So in a whole muscle, such as the biceps, muscle fibers are arranged in functional units called motor units. Remember that? A motor unit refers to a muscle fiber that a single motor unit, a motor nerve innervates. And skeletal muscles are innervated by motor axons from the central nervous system. And can you tell me roughly what the transmitter is? Chemical transmitter that drives all your muscles. Acetylcholine? Yeah. I don't know, I'm deaf, you might have said acetylcholine. Good guess, okay, sorry. All right, so, and basically, there's never a one-to-one nerve-muscle correspondence. Happens in insects sometimes, some of the lower species, but in mammals, never. So basically, the number of muscle fibers controlled by a single motor axon is determined by the dexterity of the movement. Your fingers, you're a good violinist or something, will have a small number of muscle fibers associated with each nerve. So, gross movements such as postural movements, hamstring, gastrocnemius, one nerve will control hundreds of muscle fibers. maybe even 1,000. So that's not very fine, not a very fine movement. On the other hand, one of the finest movements you have is eye position. And one nerve control, 5 or 6. Somebody's actually worked that out. 5 or 6 muscle fibers. They're very small meridians because you want real fine control. Skeletal muscle structure comes down through the ages. And there have been many theories of muscular contraction, which started out basically this. Under a microscope, if you look at a skeletal muscle, this is probably a broad one, which is nice and organized. You see in this whole muscle cell, or this is probably a myofibril, alternating patterns of light and dark bands. Bands vary in width and extend the full length of the muscle fiber. Just to go back a step or so. Oops. You look at this thing is a myofibril, and it has bands. So the whole length. These are alternating light and dark bands, and they've been given names based on their optical properties, which started out, somebody looks at it under a light microscope, and there's something dark and something light. And that's the way these things were determined. At that time, nobody had a clue how muscle actually contracted. You just saw bands. So here are several bands. Some of this is the light band here is the I band. There's the A band, which is sort of the darker region. In the middle of there is an H band or H zone. Depends which textbook you read. And in the middle there is something else of another dark pattern. And these things extend the whole length of the muscle, a myofibril or muscle cell. This is I think the fact that it's so nicely organized is probably from the problem. The names are old. There's something you have to give a name. A band is the dark region or a slightly lighter region in the center. H zone is the light region in the middle of the A band. Something called an M line, which is mostly prominent in cardiac muscle, but you also see in skeletal muscle. I bands are light regions, and the Z line, the disc, is a narrow dark line in the middle of the I band. Now the distance from Z line to Z line is called a sarcomere, and it's usually 2 to 3 micrometers in length. And all sarcomeres in a muscle fiber are identical. So I'll just go back. This is roughly the I band, the light with the dark line, which is the Z line. The A band is this guy here. I band again. This is Z line, Z disc, and the M line right here. So for years, nobody really knew what these meant, other than the fact that they were kind of interesting. And there was sort of a schematic of things that actually make these bands up. And it wasn't until after the Second World War that biochemists were able to take the proteins out of these bands and isolate them. And it was about 1945, 46, and they showed that the major proteins in the I bands and part of the A band was actin, and the thick filaments of the A band were a protein called myosin. So that's a long time ago. That's before most of your parents were actually probably born. So, the thing that they were shown many years ago was the fact that there were filaments. The thin filament was in the I band, and the part of the A band, a protein called actin. And the thin filaments are made up of, whoa. It's a typo here. Made up of actin, which is a double-stranded alpha helix polymer of actin molecules called F-actin. F-actin is associated with two actin-binding proteins, one called tropomyosin and the other one called troponin. Tropomyosin has two identical alpha helices and shadow the actin double helix. Troponin, on the other hand, is heterotrimer, consists of 3 subunits. That was kind of a major breakthrough in about the 70s. And these 3 subunits were purified, and TNT binds to the tropomyosin. You had a TNC subunit which binds calcium, and a TNI binds to the actin monomer. So these things are there. And in addition to that, it contains something called nebulin, inelastic protein, which helps anchor the thin filaments to the Z disc. So those are the proteins. There's also a couple other things which we'll cover as we go along. So this is the structure of a thin filament. These are the actin molecules, double helix. This brown guy is the tropomyosin, and the troponin complex shows this purple one, TNT, one that binds there, the TNC, which is the calcium binding protein, and the TNI, which binds to the actin filament. So at regular intervals, you have the troponins, and the tropomyosin follow this all the way to the helix. And that becomes a very important part of how muscle is activated to contract. So this is the actin filament, and just to show you where it actually belongs in the whole structure, that's the guy we're talking about right here. This one here. The actin filament. So all the good stuff on there, and additional stuff on there as well. Okay, now thick filament, which is now the myosin molecule, which makes up the A band. 10 nanometers in diameter, 1 micrometer in length roughly, are polymers of a protein called myosin 2. Okay, polymers stick together and make filaments. So each myosin molecule is a double trimer consisting of 2 intertwined heavy chains, 2 regulatory light chains, and 2 essential light chains. So that's the myosin filament, or molecule, the individual molecule, that makes up the filament. The 2 heavy chains are the things in the picture coming up. Have 3 regions, a rod, a hinge, and a head region. The rods are alpha helices. Hinge regions flare out in 2 globular heads like a double-headed golf club. And the heads that we talk about are cross bridges. They contain binding sites for actin and contain sites for binding and hydrolyzing ATP, because ATP becomes kind of important in contraction. A thick myosin filament is made up of many molecules of myosin and heads arranged to point outward, leaving a little bare spot in the middle. Now you can take these things, purify them, and reconstitute them. I can't do it, but good biochemists usually can. So basically, if you take a solution containing myosin, individual molecules, and you put it in the right conditions, things do this sort of thing. Tail arc for grade 1. So these are the myosin heads, and there's a bare spot in the middle. Does that make sense? So when you reconstitute them, that's what they look like. They actually form the filament, and the heads are raised themselves, so they're on the outside. You have a bare spot in the middle. Show you a picture. Okay. Here's an individual myosin molecule. There's your tail region, double helix. There's a hinge region, which says, depending on the conditions of the, whether ATP is bound or broken down or anything, this will actually swivel. So it sits like this, and it'll move from about 90 degrees to about 45 degrees, depending on what's going on here. So this hinge region will actually swivel, and these are the two heads, double-headed also. There's this alkali light chain and a regulatory light chain on this, on another kind of protein. In certain kinds of muscle, smooth muscle, for example, this thing gets, with ATP, gets phosphorylated, and it actually changes its activity, or its ATPase activity for activating and breaking down ATP. So this is one individual molecule, which I've drawn crudely here with one head. Two heads are a little beyond my artistic talents, but basically that's what these guys look like individually, and they form the filament. It was not that long ago, actually, when people didn't believe that there were these myosin heads were actually cross bridges or would contact the actin filaments. This was a very fairly recent electron micrograph showing the actual thick filament backbone. That's this guy here. The thin filament here, and then you can see the sort of funny little shapes here under EM, which is hard to do, hard to fix and get them. And these are supposedly the one or two of the heads of the myosin molecule. This is the first really good EM that I've ever seen. I remember going to meetings where people would show sort of funny little things there and everything. So, well, that's an artifact. Well, it isn't actually. It's the actual myosin heads coming in close contact with the actin film. So the real story is, that's roughly what had happened. So this is the myosin or thick filament. These are the two golf clubs. The reason we probably have two is sort of a safety factor. So if one doesn't bind, the other one does. And this is the actin filament. And of course, these guys are actually shown very thin here, but they're actually thicker. And basically, during contraction, these things bind to the actin filament, causing ATP to break down and move, pull these actin filaments in toward the middle or the 8 zone. Now this should blow your away here. It just shows you sort of most current schematic of what an actual sarcomere looks. This is one sarcomere. You have actin filaments, myosin filaments, actin filaments. We'll come back to this in a minute. This is one sarcomere. This from here to here. This is the A band. H band is this region here, and the M line right in the middle. Now, in addition to the proteins I mentioned, which are important in contraction, there are other accessory proteins. One of the most recent ones is a protein called titin. And it's a very large elastic protein, probably the largest protein in muscle. and anchors the thick filament to the Z disc and provides an elastic recoil. So it's like a spring. Not a big player in skeletal muscle, but it's there. It's a really big player in cardiac muscle. There's two other C protein and myosin hold the thick filament in precise alignment at the end line. Alpha-actinin makes up the Z disc, and of course, nebulin helps to anchor actins in the Z disc. So these are all the proteins that are known at the moment. And there's a couple others which I won't bother with. Go back again. These spring-like things are, of course, the titin. They're in skeletal muscle. They're like a spring. And they provide some elastic recoil. But in skeletal muscle, they're not a really big player. The C protein and the myosin hold all these things in proper alignment at the end line, and alpha-actinin makes up the Z disc, and nebulin, of course, anchors this to the Z disc. So those are all the goodies that we're going to bother with. And what I mean by that, if you look at cross-section of the filaments, this is the I band, this is the actin. H band is right here, just the myosin. The end line, of course, has these other proteins which will hold in precise alignments. And A band, the overlap, you should have 6 actins around each plasma molecule. So this is a cross-section to the skeletal muscle. Now, the initial evidence of how this actually works was photographic. And this was hot stuff in about the 60s. It's called the sliding filament theory. Evidence was photographic. Contraction, the A band doesn't change. I band is shortened, Z lines really closer together, the H zone gets smaller and disappears. So then the actin filaments must slide between the myosin, somehow like this, to shorten the sarcomere. So actin filaments are pulled towards the H zone by the cross bridge of each assumed, and a small force of moving the generator of each cross bridge. And that's actually been measured in a very artificial situation. But they figure that each breakdown of ATP gives you a force of about 5 piconewtons or a movement of about 11 nanometers, which is pretty tiny. Each force is pretty small, but in fact, if you have many thousands of active cross bridges, gives you the actual force of contraction. That's why you can lift a keg of beer with your arms, whatever. Anyway, so you need to have many of these working, but the force generated by each one due to an ATP molecule is usually very small and measured in artificial sort of situations. So in order for muscle to actually, skeletal muscle to contract, or any kind of muscle to contract, you need the following things inside next to the myofilaments, or the filaments. Of course, you need actin, you need myosin, you need the troponin, you need subunits, you need ATP, and calcium has to be greater than 10 to the minus 7 molar. I don't know if Dr. Noreen told you this or not, but calcium, resting calcium in all cells is roughly in that range. It's very low. Because calcium is cytotoxic inside cells. It starts to trigger things like apoptosis, cell death. So you want to keep the calcium low. You want the situation to occur where calcium goes up for a fraction of a millisecond or millisecond and then gets taken back up somewhere. Because calcium itself, inside cells, is cytotoxic. And you need trace of magnesium. You need magnesium because because many enzyme systems that break down ATP require magnesium and ATP to be associated. So it's a cofactor. So you need a trace. Don't need much. And if you get all of that stuff in there, high calcium, all this goodie, you get what is known as cross-bridge cycling. So the cross-bridges bind, pull, release, bind, pull, and give you the contraction. And this happens very quickly. So you need all this stuff, and assume for the minute that you do. These are roughly, your textbook has something similar, but this is roughly the stages that each cross-bridge might go through. And I want to warn you that this is current ideas. However, 2 years from now, there may be a little modification, so these things all change. But they're very current. Your textbook is pretty close as well. During the cross-bridge cycle, contractile proteins convert the energy of ATP hydrolysis into mechanical energy for and/or movement. So the first stage, let's start out saying that you get AT binds to the myosin head. And at this stage, we assume that the myosin and the actin are bound to each other. And there is a binding site on both, so they actually will bind to each other under the right circumstances. So when ATP binds to the myosin head, assuming there's enough ATP around, it releases the binding site, so the thing relaxes. Myosin head is released from the actin filament. This stage, where the ATP, or the myosin head and the actin is bound to the actin filament, is what is called, or sometimes referred to as rigor mortis. So that's when you have somebody dies, and after a few hours, the muscles become very stiff. The reason for that is ATP has disappeared, and actin and the myosin are bound. Eventually, things start to deteriorate, and things loosen up. So then, the next stage would be ATP hydrolysis. ATP is split to ATP plus inorganic phosphate and myosin. And in this stage, the myosin head will pivot. It actually moves. And that's very common in many proteins when you ATP phosphorylates a calcium channel, for example. You get a conformational change. And that's what's happening here. The thing actually changes shape. But it pivots on that hinge region. Just simply pivots. Then what you're left with ATP plus inorganic phosphate and myosin. And the myosin head now will bind to a new position on the actin filament due to the increased affinity of the myosin and ATP for actin. So then they'll bind again someplace else. Further up the line we go. When you have the release of the PI, the inorganic phosphate, this triggers a power stroke, and there's another conformational change. The thing is out here, and it pulls. So it goes from 135 degrees down to 90 again. Actin is pulled about 11 nanometers along the myosin filament. ADP is released from the myosin head, but the myosin head remains bound to the actin, the Riger complex, rigor mortis, until another ATP binds and initiates the cycle. So if you have enough ATP around, you won't get rigor mortis, hopefully. You have to be dead to do that. Okay, so that's the situation. Here's a picture I stole from a text. Next you'll need to buy or pay them. Costs a couple $100, that's okay. Here's the attached state, that's a Riger complex. There's nothing on there. ATP binds to that and releases it. And once it's split and hydrolyzed, you get a change in conformation. It's not shown very well, but you have to look, these guys are here, and then it shifts. Cross-bridge forms, and myosin binds to new position. That's the cross-bridge state. PI is released, and the thing changes conformation. ATP is released, and you end up with this bound to the actin filament, which is the right. So that's a cross-bridge. So you need calcium, you need all the good stuff. Now, as I pointed out earlier, this is for the current ideas. However, you fail this course and take it 10 years from now, these things could be a little assumed, but that's not going to happen, right? Nobody's going to fail this course. So then how do you do this? How do you activate muscle and turn it off? Question, how does the action potential in the membrane, because you have a nerve innervating, let's say, a single muscle fiber. It carries an action potential, releases acetylcholine. You get an end plate potential, which then triggers an action potential in the skeletal muscle. And these skeletal muscles generate action potentials. They're excitable cells, same as nerve cells. So the question is, how does the action potential in the membrane of the muscle cell turn on the cross-bridge? Well, something I actually do know, calcium is less than 10 to the minus 7. Cross-bridge is inactive and the muscle is relaxed. If you elevate the calcium, it'll actually go up fairly high, maybe 10 to the minus 500 times 10 to the 7 or so. The muscle will contract. So the important issue in muscle activation is calcium, which, as I told you earlier, is cytotoxic. But it's a good second messenger system, sometimes referred to as. And it actually triggers contractions. What else does the calcium do in terms of synaptic transmission? How's it release the synaptic vesicle? So everybody knows that. So that's calcium does that in many hormone secretion, all kinds of things. So this is the guy here, in the skeletal muscles, calcium, and you have to elevate the calcium. The action potential somehow must increase internal concentration of calcium near the contractile proteins. Now, in skeletal muscle, this is kind of a separate sort of issue, and cardiac muscle as well. At low calcium, the myosin ATP plus PI myosin complex cannot bind to actin. Why is that? Well, I have to go back to the structure. See what else is there. The inhibitory effect of low calcium is accomplished by the two other proteins on the actin filament. Troponin and the tropomyosin. Troponin complex and tropomyosin. The reason that myosin and actin cannot bind is that at low calcium, the tropomyosin is in the way. High calcium, greater than 10 to the minus 7, 4 calcium ions bind to the TNC of the troponin complex. TNI and TNT undergo conformational change, which removes the steric interference, moving deeper into the groove of the actin filament. Moves it out of the way. In skeletal muscle, the calcium, troponin calcium binding site has too high affinity and too low affinity. Some of those may be actually bound calcium initially, but you need to have all four. This uncovers the binding site of the actin filament and hence allows myosin and actin to bind. Then you get the cross-bridge cycle. Here's another picture which I think is pretty good. This is the region of where the troponin complexes occur at regular intervals. And here is the tropomyosin. So in low calcium, and of course this is a cross-section of the filaments. This is the F-actin binding site for myosins here. And the low calcium, the tropomyosin, and all this complex is simply in the way. And the myosin actin filament cannot actually bind it, so it's in the way of it. Now, when you elevate calcium ion, calcium concentration near the myofibrils and near the filament, then of course this thing changes conformation, moves the thing deeper into the groove, and then we frees up the binding site for actin and myosin. So then things can cross-bridge and go ahead and work. So that's the way the two proteins work. So low calcium can't bind, high calcium binding site is exposed. So these two things can actually bind. So, calcium. So the mechanism, in summary, the mechanism can be turned on by increasing calcium near the myofibrils, or near the filaments actually, and turned off by decreasing the calcium. This is accomplished by the muscle action potential. The question is how. Since there's a concentration gradient across the membrane that could come from outside, for example, the way transmitter is released. But that, in nerve cells and synapses, that is very short distances. And now you look at the situation where you have calcium outside the cell, as you're probably aware of, and the muscle cell is 100 micrometers in diameter. So how do you get the calcium in there very quickly and take it out quickly from that distance? So basically we would be walking around in slow motion if that were the case. Since there's a concentration, it could be that. New muscle definitely explains that situation. It comes from outside primarily. But in the case of skeletal muscle, which contracts very quickly, that's not the answer. It's got to be something else. So as it says there, you cannot explain the speed with which muscle contracts. 100 micrometer diameter muscle fiber contractions will last seconds instead of 200 to 300 milliseconds because the diffusion of calcium from outside takes a lot of time. So it depends on distance, and it's not enough. So in skeletal muscle, two structures exist. One which stores calcium, releases it, and removes it is located near the myofibrils, and hence near the filaments. And another one which synchronizes the release of calcium. These are structures. The structure which stores and releases calcium and removes the calcium to allow relaxation is known as the sarcoplasmic reticulum because it's muscle. It is actually the endoplasmic reticulum of the muscle cells and it serves as a storage organelle for intracellular calcium. So that's the first one. That's where calcium comes from inside the cell. The sarcoplasmic reticulum surrounds the myofibril. Has calcium release channels located near the something called the transverse tubules. We call our anodine receptors, something like processes. And it stores large amounts of calcium in a terminal cisternally bound to a calcium binding protein called calsequestrin. And in addition to that, it has calcium pumps which remove calcium from the cytoplasm, and there's a couple of this sarcoplasmic reticulum, calcium 1 and 2. Skeletal muscle has both kinds. So you have calcium pumps. Calcium pumps, in this case, are ATP dependent. I don't know if Dr. Young talked to you about calcium pump or not, but it's they're both pumps which take calcium in. They're probably not a counter going the other way, just calcium, and they require ATP. And that becomes a problem in things like the heart. When you get regular contractions, you have to have a lot of these guys. So they have to remove the calcium after each heart. In skeletal muscle, it's just after contraction. So, sarcoplasmic reticulum. This is a muscle cell showing the muscle sarcolemma or plasma membrane. It generates the action potentials. And these guys here sort of got all the little holes in the sarcoplasmic reticulum. And it surrounds each individual myofibril. And of course, if you blow up a region of that, you have something called a tubule. The sarcoplasmic reticulum, so you're taking this area here, looking at it, this is where all the calcium is stored, here and here. And so it's located very close to the myofibrils. Inside here are tons of calcium pumps. You take calcium back up. And this shows you shed disc, and of course this is the structures. Most of the calcium is stored in these areas here. So now the calcium storage areas are very close to the contractile proteins. So, hence the sarcoplasmic reticulum is a constituent of the muscle contracting relaxing system. Calcium may be applied to the contractile protein, allowing muscle to contract and be removed very quickly by the pumps, allowing muscle to relax. So the sarcoplasmic reticulum speeds up contraction in skeletal muscle because calcium has short resistance to diffuse, roughly about a quarter of a micrometer as opposed to 500 micrometers. So most types of skeletal muscle contract and relax very quickly. We'll continue on with what is now the synchronized